So, once again, to remind you that we won't have a lecture a week from today. It will be lecture on Tuesday, but we're going to travel next Thursday. And so we'll have a makeup class on the following Wednesday evening. Okay? Yeah.
I have a class at that time.
No worries, we'll work it out. We will have that makeup lecture, and we'll have our exam on the following Wednesday after that. And we'll talk more about the exam as it approaches, but it will cover through this problem set and through today's lecture. Okay? It will be an in-class exam. It won't be a take-home exam. Okay? All right. Well, so last time we talked about this phenomenon that's very important and related to the subject of perturbation theory in the following sense. We have some situation in which we're looking at the Hamiltonian as a function of some external parameter. And as a function of that parameter, we know that the eigenvalues of the problem will generally change. Okay? And we could try to solve that in perturbation theory if say, H1 is a small Hamiltonian compared to H0. This lambda, by the way, is not the same lambda that I was using in terms of the bookkeeping. We call it anything you like. It's just some external parameter, like a magnetic field strength. Okay? Just doesn't really matter what it is. Anyway, the point here is that there could be, if you just were to think about it in certain situations, it might be the case that what was previously very far separated energy levels, where we didn't have degeneracies and we can do perturbation theory in the non-degenerate manner. At some critical parameter, those levels can approach each other very close compared to the energy scale associated with H1. Okay, and in that situation, we really need to think about degenerate perturbation theory in that near degenerate subspace. So the levels you might think they might cross, but in fact they don't cross typically unless those two levels, unless there is no off-diagonal matrix element of the Hamiltonian that mixes those two levels. Then they really would cross right through one another in terms of the energy spectrum. But typically they won't. And you get this kind of phenomenon of what we call the avoided crossing. Okay? And we can easily analyze that problem because it is restricted to a two-dimensional subspace. And this gives us an opportunity to emphasize an important point. That is not just the case for this problem of the avoided crossing, but it's a generic situation. If we can restrict the Hilbert space to two dimensions, then it is isomorphic to a spin 1/2 particle. So everything that we can kind of think about relative to what happens for a spin 1/2 particle describes everything that's important in the context of this two orthogonal states. Doesn't matter, it has nothing to do with spin necessarily, right? They could be two orbitals of a molecule. It doesn't matter. They're two orthogonal states. When we restrict ourselves to that subspace, it maps one-to-one isomorphic to spin 1/2. And any Hamiltonian, we know, can always be decomposed in this subspace, as you say, restricted to that subspace, as an operator that looks like some amount of identity operator and some amount of sigma x, sigma y, and sigma z. And that looks just like a spin in a magnetic field. So everything, all quantum dynamics of a two-dimensional Hilbert space is a spin 1/2 particle in a magnetic field and nothing else. Okay? So what we could see is in a matrix representation, with respect to these energy levels, I'm calling 1 and 2, we have a 2x2 matrix. It has diagonal and off-diagonal elements, and we map that, well, no, sorry, it should be, of course, there's some, identity part, plus that. There's always an identity part. Well, it's not always, it depends how, the identity part depends on the average of these eigenvalues. If that average is 0, then the identity part is 0. But we don't care about that identity part. That's an overall shift. We care about this part, which we just mapped. We said this is what we had for a spin 1/2 particle in a magnetic field, or this is the Langmuir precession frequency around the local magnetic field. And we can then see one-to-one mapping between these parameters of this Langmuir precession frequency, which is proportional to the magnetic field, as we wrote last lecture, with some gyromagnetic ratio. So sort of the Z component is related to the energy difference. That's what we call the detuning, and the transverse components of the magnetic field relative to the standard quantization axis are related to the real and imaginary parts of the off-diagonal matrix elements. Okay? This is really important. It's so useful. It's something that's not covered in a lot of standard. Koen-Tanuji's book has a great chapter on this in volume 1. I encourage you to read it. It's really good. But it's something that it's often missed in sort of standard quantum chemistry, because this kind of, it's just so often we just reduce our quantum dynamics to just 2 levels, and then everything we know, I learned in kindergarten, when I learned to share and do spin 1/2 particles. All right, so one of the things that we studied that we said last lecture is that we could look at a situation where we're changing this external parameter as a function of time, in which case we know that if we do that change slowly enough, whatever slowly enough means, that if we started the system in one of the local eigenstates, meaning at whatever value of the parameter, for example, it was in this state 1, then as we do that, it will adiabatically follow. Of course, in this case, as it goes through the crossing, it goes from having kind of 1 character to 2 character. Okay? And in between, right here, right at the crossing point, we have an equal superposition. I didn't mention that, but that's what's written here. It's an equal superposition of 1 and 2, with a phase that depends on whether it's real or imaginary, the off-diagonal elements. If it's a real off-diagonal element, then it's just symmetric and antisymmetric. If it's pure imaginary, then it's got an I in it. If it's in between, then it's e to the I5. But we go through this crossing. If we do it slowly enough, then we stay adiabatic. If we move too fast, then, well, we can't adiabatically follow, and we go through this crossing, and we end up on the other state. We end up back up here, still in 1 character. And we looked at that, just thought about a spin in a magnetic field like we did last semester. And we thought about, when we studied the adiabatic theorem in homework, right? So this is exactly the same problem, but now it's not a spin, it's just a pseudo-spin, if you like, okay? And in particular, what we see is that the condition for adiabaticity was that this parameter should be big compared to 1, okay? And that parameter is related to the strength of the transverse magnetic field, which is the thing that allows us to go from up to down. So that's the off-diagonal coupling between 1 and 2. And it's also related to this, the way in which the energy difference here, which is like the longitudinal magnetic field changes as a function of time. Okay? So this is a dimensionless parameter. And it's the parameter that determines whether or not the system stays adiabatic. All right? And so, for example, if I have, it depends both on this energy. Of course, that energy determines what this gap is, right? Because right at this transition, right at the crossing point, the detuning is 0, right? Because at that point, these guys are degenerate. E1 equals E2. So this gap is related to this. So you need to have the gap, the mixing, big enough. That's one thing you need. And the second thing you need is you need to change the system slowly enough. So if I have two systems, you notice it looks like the difference of the slopes. If you have something which is very shallow, this is E1 and this is E2, if they don't change very much as a function of time, then I don't need as big of a gap, and I'm guaranteed to stay adiabatic. On the other hand, if the two levels come up with very different slopes, then I better have a pretty big gap in order to stay adiabatic. So it depends both on the size of the gap and also how fast the energy levels are changing as a function of parameter. Both those things matter in this adiabatic parameter. Okay, so it's like, can I, you just sort of think about it as going on this road, how fast this curvature is kind of related to that, the difference of the slopes. And this particular form of what is the probability for staying adiabatic versus going diabatic is known as a the Landau-Zener formula. And it's a particular case that one can solve when the sweep through this crossing is just linear in time. Okay, so if you just change it linear in time, you could solve that problem, solve the time-dependent Schrodinger equation. You could do it, and you find that asymptotically far past the curve, that the probability to go diabatic is exponentially small with this adiabatic parameter. This idea, this is sometimes known as Landau-Zener tunneling. I don't like that term. It's nothing to do with tunneling, but it's what people call it.
Tunneling implies going from one state to the other, right?
Well, tunneling has to do with classically forbidden dynamics. Okay? That's what tunneling is. That's how I would define what tunneling is. So if you have a turning point of a particle, it can't go into a regime where the kinetic energy is less than the total energy. This is not, I mean, this is perfect. I mean, the same thing would happen for a spin. Moving, I can go from here to here. There's nothing non-classical about that. That's why I don't like that term. Okay? All right. So, that's our review for last time. All right. Let's turn our attention then to something else. So, I want to look now, we're talking about perturbation theory, and we're going to talk about a particular application of perturbation theory. The fine structure of high energy. So, when we when we wrote down the Hamiltonian that described the hydrogen atom, the interaction of the proton and the electron, we did so in an approximate way. We had the non-relativistic hydrogen atom, which I'll call H0. Center mass frame, where the center mass is basically at the proton. Okay? So that's what we did. And what we want to think about now are relativistic corrections. Okay? So how big are these terms? Well, so let's review what we looked at in homework with the kind of the characteristic scales are. We can estimate how fast is the electron moving relative to the proton in a hydrogen atom, just from dimensional analysis. Okay? So let's take a look at that again. So what we have is, well, you know, our characteristic energy is the Hartree. And so there's a characteristic time given that energy, which is h bar over the energy. Okay? So that's A naught over E squared h bar.
Should the H bar.
Sorry, in the upstairs, yeah. And A naught, which is h bar squared over me squared. No, it's h bar over me squared. So this is hold on a second. I don't have this in my head. Yeah, that was right. So what the heck did I do wrong here? Oh no, okay. No, sorry. Got myself confused for a moment. That's correct. So the characteristic speed of the electron is the characteristic distance over the characteristic time, which is E squared over h bar. That's correct. Okay, so that's the characteristic speed. How big is that? Well, what we know is that in relative to the speed of light, that's a dimensionless constant. And that speed is approximately relative to 1 over 137th of the speed of light. So it's not moving at the speed of light, but it's moving pretty darn fast, okay? So it's, you know, a percent. You know, this is fast. So relativistic corrections are not nothing. They're perturbations. So it's a perturbation. The relativistic effects will be perturbations, but they're not going to be nothing. Okay? It's not like they're completely negligible. Like, you know, the correction of electroweak couplings to shifts in the end. We can measure, but they're tiny, tiny, tiny. All right, so what kind of relativistic perturbations do we expect? Well, one thing that we see here is when we wrote down the interaction between the electron and the proton, we only took, this is only the electrostatic interaction. But of course, there's an electron that's moving. So there are magnetic effects, and we've ignored them. Okay? So there's a magnetic effect. They're relativistic corrections. Right? Because, you know, the force on a charge, Q, depends, for an equal strength of electromagnetic field, they're down by the order of V over C. All right? Say in an electromagnetic field where E and B have the same magnitude in CGS units. In SI units, of course, B is E over C, and then there's no incidental section. All right? So what is it? Well, so we have this situation where we have, you know, the proton here and the electron just thought of as a kind of Bohr atom moving around. And of course, since it's moving, we can ask the question, what magnetic field does the electron see in its rest frame? Okay? Because the force exerted on it depends on what the local magnetic field is in its own rest frame. So what is the magnetic field seen in the electron frame? Well, that depends on what the magnetic field, what the electric field is in the lab frame. So if V is the velocity of the electron relative to the proton, that's to say that's the frame that we have to go to, then everyone remembers from 406 or equivalent that that is what the magnetic field is. The lowest order in one over each other. Usually there would be a relativistic gamma here, but to first order in V over C, and we're going to keep the lowest order terms in V over C as a perturbation. This is what we have. Okay. So that is then equal to the electric field is the field coming from a point charge, right? And that is the proton's charge times 1 over the distance squared times
Should there be a mass in the BC over there?
No, that's correct. I believe that's correct.
Divide A by T, the mass doesn't vanish.
No, I just wrote this A naught over T.
Oh.
Okay. All right, so what was it saying? This is in the direction R squared, in the direction, right? That's the electric field. If this distance, if this is the vector x, okay? And so this is then equal to minus E over mc times mv crossed into divided by r cubed. This is the momentum. Momentum cross position is minus the angular momentum, r cross p, right? So this is equal to E over mc L over r cubed. Yes, Steve.
So that V is the velocity that the lab sees.
It's the velocity of the electron
Okay, in the lab.
in the lab.
Okay, thank you.
So now I go to that rest frame, and in that rest frame, this is what the magnetic field is.
And so that L is the angular momentum of the proton? Or I guess
No, it's the in this. You see what it is? It's the angular momentum
Okay,
of the electron.
okay.
So this is the electron's angular momentum.
The magnitude of the vector x is r? Or
Yes,
is
that's
it
correct.
Okay.
The magnitude of the vector x is r. That's what we always say. R theta phi. X is just x, y, z. Sure. Alrighty. So what do we got here? Right. So this is the magnetic field. Does this make sense? Well, I can kind of look at it in, is this what we might have expected? There's another way to look at this, which is say, let's sit on the, you know, I'm the geocentric guy. Instead of the Earth going around the sun, I think the sun's going around me, if I'm sitting on me, right? Because it's all about me. And so I could say, well, there's this electron here, and in its frame, it sees the proton going around it. So there is a current loop, right? And if I have a current loop, I ask you, because you all just did the prelims, what is the magnetic field at the center of a current loop? Well, I'll have to study that. But the magnetic field, if I have a current loop, right, you know, it has this kind of magnetic field, right? Looks like a magnetic dipole. And right at the center, the magnetic field, if this has a certain magnetic dipole moment, then the magnetic field at the center is the magnetic dipole moment over r cubed.
Is it singular though, or no? I mean.
No. At the center of the loop. This is not a point charge. This is a loop of current.
I mean, okay.
So here I am at the center. The magnetic field is not infinite there.
Okay, I mean, okay, but R3 is just not zero though. No, because that's just a constant radius, or the.
This is the radius.
Okay.
This is the radius. This is the rate. This is the distance here.
Thank you.
Right? And the magnetic dipole moment, we remember, is this, because we studied that. So you plug that in and it all works. Okay. So this is the electron's angular momentum. So given that there is a magnetic field at the electron's position, this is it. I ask you, what is the interaction energy that is arising due to the existence of that magnetic field?
Do we need to rewrite the momentum in, like, with the A field, or no? Like we did
No,
with the,
we don't,
okay.
because, I mean, at the end of the day, I mean, we do know, of course, that we can always write for a constant magnetic field, there's a diamagnetic term and a paramagnetic
Okay, so
term,
just
right?
the
And it's in this case, because we're just talking about this one point electron, it's only the paramagnetic term that matters.
So the mu dot B?
It's mu dot B, right? So it's mu of the electron minus mu of the electron dotted to the magnetic field seen by the electron. Okay, so that's the interaction energy. And that is equal to the mu of the electron is minus twice the Bohr magneton times the spin of the electron in units of h bar, dotted into this. And this is equal to, remember the Bohr magneton was E h bar over 2mc. So this is equal to, if I multiply this top and bottom by h bar, and then top and bottom by 2, this is dotted into 2 mu b L over h bar times 1 over r cubed. And all of these are operators. Now,
Another mu b?
What's that? Sorry. So this then is equal to 4 times the 4 magneton to the 4th power over r cubed. And I'll write this as little l dot little s, which is, this is in units of h bar. Okay? I'm sorry, not to the 4th. Square. Pardon me. Okay. All right. So, this interaction, I'm gonna, instead of calling it this, I'm gonna call it SO for spin orbit. This is called spin orbit coupling. That is to say, the spin of the electron is coupled to its orbital angular momentum through the fact that it's moving through through an electric field. In its rest frame, it sees a magnetic field. The strength of that magnetic field depends on what its orbital angular momentum was. And that then interacts with the spin and gives us this spin orbit coupling. All right? Very good. Let's put this in dimensionless units. Okay? So, we'll write r in units of the Bohr radius. This is our dimensionless unit. Mu b is equal to what? Well, we just said mu b is equal to E h bar over 2mc. Okay? Now, if I wanted to write this in atomic units, then atomic units don't have the speed of light in it. They're the non-relativistic thing. So I want to write this in units of a dipole moment. So in units of E over A naught, E times A naught, which is the electric dipole moment, just dimensionlessly. In CGS units, the magnetic dipole, electric dipole, same units. Okay. Then this is equal to E h bar over 2 mc A naught. And I can plug in for 1 over A naught and E squared over h bar squared. And then I have the E over here. So that cancels that. That cancels that. I get 1 canceling that. And I get E squared over 2, or half the fine structure constant. Why? I mean, I went through all this, but the thing to remember is that any magnetic effect is going to be down from an electric effect by 1 power of V over C, because they all depend on that. So the characteristic magnetic dipole moment is, compared to the characteristic electric dipole moment, is reduced by 1 power of alpha, which you did in your homework. Okay? I did to somebody's madness. So what we have is that in dimensionless units, the spin-orbit interaction is 4 alpha squared over times L dot S over R cubed. You know, this is in units of the Hart tree. So from now on, I'm going to write this all in atomic units, get rid of the atomic units. Okay? So this interaction energy is reduced compared to the binding energy by alpha squared. It's of order alpha squared. It's the lowest term. All right? Very good. All right, so now let's look at how this, we write the total Hamiltonian as H0, that's the standard Hamiltonian for that we wrote down for the binding of the proton to electron, and then the spin orbit interaction. Okay, so this is my perturbation. All right. So I want to do perturbation theory. Okay. Now, on the ground state, this has no effect, right? Because the ground state has L equals 0, so there's no spin orbit. So this term does nothing to S states. Remember, we are with this annoying notation that S means two different things in atomic physics. We could have the spin S, or we could talk about S states, and those two S's have nothing to do with one another. This means L equals 0. All right? Sorry, I didn't make it so. All right. So, we now look at the first excited state. Well, it's actually states, because it's a degeneracy for n equals 2. There's the 2s, which of course I can throw p. There's the 2p with n equals plus 1, minus 1, 0. Right? Those are the four states here. Now, there's this, so this we have to think about degenerate perturbation theory. Degeneracy. Okay? So, how do we do that? Well, we have to diagonalize the spin-orbit interaction in this subspace. Okay? Now, before I do that, I forgot one important point. This is actually wrong by a factor of 2. And this confused the founding fathers for a long time because they couldn't get this down. They saw this fact. It's one of the reasons why it was a long time coming on trying to understand the fine structure and the whole notion of spin is that there are all these factors of 2 floating around. There's the anomalous G factor of the electron, and then there's another factor of 2 that's coming from the following effect. I cheated. I cheated because I went to a non-inertial reference frame when I did this transformation. So this formula isn't exactly correct when you go to a non-inertial reference frame, because of course special relativity is about inertial transformations. And some guy named Thomas, who I don't know who he was and what else he did, but he's famous for this, solved this problem of thinking about what happens to a relativistic transformation on a rotating body, relativistically when you go to another rotating frame. And what you find, and it's a complicated calculation that you can read about in Jackson, that there is a correction. There's a correction factor here of a half, which is known as Thomas precession. And so really, there's a half here, there's a 2 there, and there's a 2 there. Okay? That's coming from the non-inertial transformation. All right, so now we have the correct spin-orbit coupling to lowest order in alpha, and we have to now diagonalize this. We could do that. We can write this out. So remember, what is this? the basis here, we have the basis states are N, L, M sub L, right? Those are our H0 eigenstates. And those are equal to the radial and spherical harmonic separation, right? So we can write out L dot S. So these are not quite the basis states, because these are the basis states without spin. So before I do that, I really should have this tensored into the spin as well. So these states, we really have a doubling. There are 8 sublevels. That's because now we have to include the spin explicitly because it's interacting, okay? So we can write this out. This is the uncoupled basis. That we talked about earlier in the semester, the product basis. And we could diagonalize the Hamiltonian by looking at L dot S, which is, of course, Lx tensor Sx plus Ly tensor Sy plus Lz tensor Sz. Write out this operator as a matrix in this basis and then diagonalize it. We could do that, but we're not going to, because we could do this much more simply by a trick that we're going to use over and over and over again. And that trick is to note the following. Whenever you have a coupling of two angular momentum like this, a dot product, L dot S, or J1 dot J2, then note the following. Let's define J as the total angular momentum of the electron. Okay, this is L tensor the identity plus identity tensor S. Okay, it's the total electron angular momentum in units of H bar. Now note, what is J dot J? Also known as J squared. Well, that is L dot L, which is L squared, plus S dot S, which is S squared, plus twice L dot S. Okay? Which means that the operator L dot S is equal to a half J squared plus S squared. No, sorry. It's J squared minus L squared minus S squared. Right? So, this operator is automatically diagonal in the coupled representation. What is the coupled representation? Let's remind ourselves about that. So the uncoupled representation were simultaneous eigenstates of L squared, Lz, S squared, and Sc. right? That was the uncoupled representation. The coupled representation are simultaneous eigenstates of the total angular momentum magnitude squared, and then the individual guys, and JZ. Not Dr. So, this operator commutes with all these guys, right? So if I, instead of writing the basis of eigenstates in the uncoupled representation, if I take the appropriate superposition of these basis states such that I couple these together to give a total momentum J, they are automatically eigenstates of L dot S. So, the new zeroth order eigenstate are denoted by N, L, and J, and J, instead of what we had before. We had N, L, and L. Well, I guess I have S in there too, but of course S is and J. Right, that's what we had before. Take out the old, bring in the new. So this was the uncoupled representation of orbital and spin, and now we have the coupled representation. Okay? And these guys, of course, are superpositions of these guys. But if they're superpositions, all with the same end, well, they all have the same energy. It doesn't matter. Okay? So, in that basis now, we can calculate what is the first order correction, spin orbit correction, for these given. Of course, it doesn't depend on MJ, so and S is always fixed, so we never just don't write it down even. S is this S times S plus 1. Well, I'll just put it there for now. This is equal to, that shift is equal to whatever this 2 alpha squared times, well, I'll write it this way. This is N, L, NJ, let me write it in that order, because it's the typical order we would write it in. NJ, L, S, MJ times the spin orbit. This is first order perturbation theory. It says to find a first order correction, you take the expected value of the perturbation in the zeroth order state. Now the one that is the eigenstate of this. And that is equal to, according to this, twice the fine structure constant squared. Then I have 1 over R cubed expected value. Just write it that way. And it's only the radial part that matters. The angular part doesn't affect that. That's the radial integral. And then we have the angular parts. The angular parts are that. And they are equal to the half. Well, yeah, good luck with that. Somehow these units should work.
Wait.
I'll figure it out. There's some factors too, I hate that. But a half, and what is the expectation value of J, the operator J squared? J plus 1. Thank you. because it's an eigenstate of j squared with eigenvalue jj plus 1. So we have jj plus 1 minus l plus 1 minus s plus 1, which is a half plus 1. All right, which is 3/4. And now I say, I don't know why this is off by a factor of 2, but it is. Oh, I know where. There was this alpha over 2, right? And I have to square it. So that's alpha over 4. Write in the notes. Never trust these videos. All right. Moving right along. So, what do we have? So, which states, by the way, are mixed amongst these together with the fact that we have spin up and down in order to get the new eigenstates?
Rough states, the one that's down with L and down with spin.
All the n's here are mixed with these guys, depends what nj is. But the point is that only the p states with given, I mean the s and p states are not mixed, because L is a good quantum number, right? So these states here, for example, we have what we now would call the new states, new notation. We define these as n L sub j with the given mj. That's the notation. This is spectroscopic notation. So for example, we have the 2p with a given j, an mj, and a 2. So what are the possible values of j, by the way? J is the total angular momentum. We're adding, in this case, L equals 1. So for L equals 1, S is a half. What are the possible values of J?
1/2 or 3/2.
1/2 or 3/2, right? Because J goes from L minus S to L plus S. So we have a 2p 1/2 with Nj equals plus or minus a half. And we have the 2p 3/2 with Mj. What are the possible values of Mj?
Plus or minus 3/2, 1/2.
Minus half, right? They go from minus 3/2 to plus 3/2 in integer units. So the 4 states, these are the 4 states. Of course, these guys, this is doubly degenerate because the energy doesn't depend on m sub j. And this is quadruply degenerate, if that's a word. I'll make it up. All right. And of course, we have the 2s 1/2 with mj equals plus or minus a half. Yeah,
I'm sorry, that line with the 2 alpha square, starts with the 2 alpha square.
this is all multiplied together.
Okay, thank you.
Yes,
Okay.
all multiplied together. And that should actually be, as we said over there, over 2. So, what we have then is the following. Due to the spin-orbit coupling, we had n equals 2, which had the 2s and the 2p, right? There were, in the absence of coupling, this is 8-fold degenerate, because there are 3 m sub l's 1 m sub L, and then spin up or spin down. So there are 8 degenerate states. We put on the spin-orbit coupling. The S state doesn't change. This is actually a product of the 2s with m sub L equals 0, and spin up and down.
So that's what we call the stretch state?
These are stretched in a sense, yeah. They're different for this manifold, because there's only one, there's only m sub L equals 0. Then we have the states that, depending on the value of J, the bigger value of J has a higher energy than the smaller value of J. So we have a kind of splitting that looks like this, where we have the 2p 3/2 and the 2p 1/2 orbitals. Okay? Now, this splitting, if you go through some of the algebra, what you find is the following, that this energy over here, how I wrote it, the spin orbit energy as a function of NLJ, in this case, where J is L plus or minus a half, okay, is equal to, in general, if you write this in, over 4, the expected value of 1 over r cubed in that state, L, when J is equal to L plus a half, and minus L plus 1 when J is equal to L minus a half. Okay, just plugging that into J is equal to L plus a half, or J equals to L minus a half. Doing that algebra. This thing we solved using the Feynman-Hellman theorem, and we found in dimensionless units that this is equal to 1 over the principal quantum number cubed, L plus 1, L plus a half. All right. So, now, one thing we have to note, though, is that we're doing perturbation theory. We want to keep all physical effects that are of the same order in output. And the effect that we just included was the spin-orbit coupling, which came from the local magnetic field seen by the electron, right? But there's another effect that's natural. If we're thinking about relativistic corrections, there's the corrections to the kinetic energy as well, right? So there is a relativistic correction to the kinetic energy. And what is that? Well, for a free particle, right, the energy of the system is the square root of the rest mass energy squared plus the momentum contribution to the energy, right? And that is equal to approximately mc squared plus p squared over 2m minus p to the 4th over 8 m cubed c, m cubed c squared, when you do that plus dot dot dot, when pc is much, much less than the rest mass energy. Okay? So there is a rest mass contribution, which is just a constant here. This is the non-relativistic kinetic energy, and this is the first order correction in the, so this is a correction, first correction
convention is units.
Well, so one way to look at it is the following. So the lowest order, so the first correction, is an energy eigenvalue. We'll call this the kinetic energy term. That's equal to minus the expected value of p to the fourth. It's only an angular integral, I mean a radial integral, though it doesn't depend on the angular coordinates at all, because this is the magnitude squared squared. Bless you. And the trick here is to note that this is equal to p squared acting on NL. That vector inner product with itself. Okay, now note the following. P squared acting on this state over 2m is equal to the total, these are the zeroth order eigenvalues, so it's this minus the potential. Right? Because p squared over 2m, or I'll write it this way, minus, yeah, I'll just write it. P squared over 2m plus v is what I'm calling h naught. If I act this on this zeroth order state, I get the energy eigenvalue. This is equal to minus e squared over 2a naught, 1 over n squared. Right? So, let's put that together. I'm going to get rid of the units soon. That tells me that the norm of p squared acting on this is equal to 2n squared times the expectation value of e sub n minus v squared. So that's 4m squared, en squared minus 2en, the expected value of v, plus, in this state, plus the expected value of v squared in this state. Okay. So my first order correction to the kinetic, and I'll go to the next, back to the front board over here. Ugh. So what we get is that the first order correction to this state due to the kinetic energy, putting all of that together, is equal to minus 1 over 2 mc squared times e sub n squared minus 2 e sub n, the expected value of v, plus the expected value of v squared in that state. Okay, now let's factor out the units. It says units of energy because this has energy squared in the numerator and energy in the So I'm gonna, remember E sub n is what we wrote over there, minus 1 over 2n squared times the Hartree. Right? Now, let's see, what can we say? This is a little aside over here. I claim that the Hartree energy is equal to the fine structure constant times mc squared. Well, you can see that, because if I plug this as E squared over H bar C, oh Lord, this is M E squared.
I think E squared or A naught, if you just square alpha, I think it might work.
It's alpha squared, huh? Yes, okay, thank you. It's alpha squared. There's a missing energy in my, I know that there's these ratios of fine structure, but there's one that I'm missing.
You won't have back with E squared under, yes.
So, let me just think about this for a moment. No, that's correct. That is correct. Yep. All right, so with that said, if I divide out this E squared over A naught, what do I get over here? So let's write all that down. So this then is equal to, because of this MC squared, I get alpha squared over 2. This squared is 1 over 4 n to the 4th. Minus this times that, 2 times that gives me n squared, times the expected value of the potential in dimensionless units. And then I get the square of the potential in dimensionless units. Okay? This algebra is not particularly interesting. It is what it is. All right? You just have to do it. Who cares if it's right? You get it right in the end. The ideas are the important point. Okay? So let's not fret over it. All right. The point here is the following. We have these integrals. We've done them in the past. You put it all together, and here's what you get. This is equal to alpha squared over 2 times minus 1 over n cubed plus 1 plus 3 over 4 to the 4th. Okay? That's just plugging in for these expectation values in that we've solved previously and doing the algebra. So, for the case of the P states, we can put all of this together. Taking that form that we have in the back corner there for what the spin orbit correction is for L not equal to 0, we have the total energy shift to first order in these guys is equal to the spin orbit guy plus the kinetic guy. Okay? And when you do that, you get the following. You get alpha squared over 2 times minus 1 over n cubed L plus 1 plus 3 over 4 n to the 4th when j is equal to L plus a half. And you get alpha squared over 2 n is this right? Yeah. Let's take the n cubed out. Make this like this. Alpha squared over 2n cubed minus 1 over L plus 3 over 4n when j is equal to L minus n. Fine. Yep.
Is this only for L equals 1?
No, it's for anything other than L equals 0. In what we solved there, I mean, firstly, so for the spin orbit coupling is 0 for L equals 0. So the spin orbit coupling that we derived in that back corner was for any L other than L equals 0. Secondly, this is true for all L, because there's no assumption here. Okay? But what I've done is I've put together the spin orbit contribution with the kinetic contribution for the cases where L does not equal to 0. And you get this. Yeah?
Shouldn't we had to diagonalize p to the 4th in the degenerate space of n is equal to 2 to get the first order?
We get the situation, we do have to diagonalize it, but it's the same for all angular components, okay? So it's diagonal with the same, we have diagonalized it. In other words, the total space, we said was this, right? Which is equal to, there are radial integrals, and then there's angular. This p to the 4th only has elements that are diagonals, no off-diagonal elements between anything here. So they're all the same. It only depends on the orbital motion, and it only depends on the radial. So that's what we did. All right, but now I'm coming to a couple of punchlines here. Wading through this algebra is no fun, but I want to get to the main points. Okay. Notice that this actually has one form. I don't have to write it in terms of this 2 thing. It's equal to this. This is equal to minus alpha squared over 2n cubed 1 over j plus a half minus 3 over 4n. No matter what L is. Because these two terms are the same. It's j plus a half. Okay?
Is the minus?
I factored out the old minus sign. And get that. Okay? So what we see here in this particular form of the shift, the fine structure shift, depends only on J in this case.
So that's the fine structure shift energy?
Yep, that's what this is. Now, this actual formula can be seen as this is the lowest order correction to the non-relativistic energy by expanding the exact, quote unquote, Dirac equation solution. So the Dirac equation is the relativistic Schrodinger equation for the electron and positron, of course, because in the relativistic theory, you have to have both the particle and its antiparticle, and you have a equation for the coupling of the positron and the electron, and you can solve the Dirac equation. And the Dirac equation gives the following solution. It finds that, in fact, as expected, the energies here only depend on J and N and not L independently. Okay? So you take that solution, you expand it to lowest order, and you get mc squared minus alpha squared mc squared times 1 over 2n squared. That's, of course, the 0th order solution. This is the Hartree, plus this. So we can understand the solution if we had solved it exactly and then expanded it to low orders in alpha. However, what about the S states? Well, it's a little more complicated, actually, because if you take the Dirac equation and you try to expand the equation to get perturbations, you will find the spin orbit term, you will find the kinetic term, but you will find one other term, which is known as the Darwin term. Now, Darwin, I found out, I had no idea, was actually the grandson of the famous Darwin. Yes, he was a physicist. But anyway, that term cannot be understood as coming from the, some simple perturbation. It's coming from the idea that there are positrons and electrons. And in the Dirac equation, what you find is that if you try to look at just the electron alone, you find that it has this trembling motion, which is known as Zitterbewegung, which is the German for trembling motion. And that's why we call it that. And the electron is, in some sense, not well localized. It's really not right to think about it as a single electron theory. It's electrons and positrons, and they constantly there's virtual excitations and de-excitations. When you do that, you find that this is true for the S states as well. So I just want to conclude with the following thing. So while I drew this picture over here for the splitting, just through the spin orbit, when you add in the corrections that are due to both the kinetic energy and which shifts all these guys, and the Darwin term, which is the S state, you find the following. Once again, these guys become, so this state goes down here, this state goes down here. The 2p1/2 is once again degenerate with the 2s1/2. And then the 2p3/2 is up here. Because the energy depends on J, not L. And these guys have the same J. And this is known as the fine structure split. Now finally, turns out that's not the whole story, because this relativistic theory didn't account for the relativistic quantization of the electromagnetic field. There are vacuum fluctuations in E and B, and that affects things to this same order. And what it does is it slightly shifts the 2s relative to the 2p, and there's a shift here that's due to vacuum fluctuations of the electromagnetic field. They're also of the same order, and this shift is known as the Lamb shift. After Willis Lamb. So after we had this lecture when I was a graduate student, I was sitting next to a friend of mine who was a brilliant guy who wrote a haiku. And my professor was Dave Jackson, the guy who wrote the text. So this is the haiku. Jackson is the devil as he shifts the baby lamb. The hell Adams dance.
That's not a haiku. That's not a haiku. The first line had 6 syllables.
I'll work on it. Thanks for ruining it, Stephen.
No problem.
All right. Have a good rest of your day.